It's in between the two events. So the point is that models, it's just a mathematical way of modeling time change, things that change with time. And the roots of this come from ordinary differential equations. So how many of you have never seen the existence of Newton's theorem for differential equations? Okay, so I'm not going to state the theorem, but I'm going to tell you what it tells you. So it says the following. So the existence and uniqueness theorem for ordinary differential equations. I'm going to tell it my way. So look at the equation x dot equals f of x, where here x is in thinking Euclidean space. It can be a manifold. You can make this fancy in all kinds of ways, but think about it just in Euclidean space. So we're modeling the state of a system by a vector. There's a certain number of numbers that define the state of the system. And x dot is the time derivative. This is something that changes with time because it's actually supposed to be a function. And so and we're talking about an autonomous differential equation, autonomous system, which means that the time derivative at a particular place is always the same. So this doesn't change with time. It's a function of where you are. So another way of saying that, of course, fancy language. All of you, those of you who are in 217 would say, oh yes, the vector field. Well, it's the same thing. Whether the vector field is telling you the velocity at that point, that's exactly what we're giving you here. Okay? So you can think of this as a vector field in Rn, and we're looking at motions tangent to it. And what the fundamental theorem says, fundamental theorem says is, so first of all, let's assume if f is nice. And nice means, for example, Lipschitz. I think continuous is in it. No, continuous is not enough, but Lipschitz is. Or certainly if it's differential, or C1, or C. Then for every, take any point in the plane, in Rn, in plane space, there's a unique function from some interval, just think that way, but some interval, let's say some interval from minus t to t, where t may be infinite, in fact, you hope it is, to Rn. So that two things happen. Phi of 0, the starting place is x0, and x equals phi of t solves this equation. Okay, in other words, it's a path that moves in such a way that its velocity, wherever it is at any time, its velocity is given by value of this function at that place, or that vector field. And what this leads to in really reasonable cases, when you have what's called a complete vector field or complete differential equation, is this t is always infinite, and that gives us a flow. So what's a flow? It means something like this. Well, technically, those of you who are geometric group theory, it's an action of the reals on R. And what that means is, I'm getting a little low here, means I've actually got something like this, a family of homeomorphisms from Rn to Rn. For all t, phi t is a homeomorphism. In fact, better than that, it's going to be, you expect it to be, as smooth as, just about as smooth as this. Okay, so we have this family of homomorphisms. Think of things as just flowing with time. So we start somewhere with time intervals, and it's a stationary flow. The lines don't change. The flow lines don't change. So that's sometimes called a continuous dynamical system. Continuous meaning that the time is continuous. Now, these things have been around for hundreds of years, but then in the late 19th century, Poincaré, who invented topology to do this stuff actually, was looking at the n-body problem, which, by the way, is not complete. That's been proven, at least for 4 and more. But anyway, he's looking at the n-body problem, and there's all kinds of complicated things. And one thing he did was to think about the following. Let's start drawing pictures. So I've got a flow, and Well, actually, first of all, so we can get discrete systems. Okay, and how does it come about? One of two ways. One is sample t just in the integers to get an action of t, of 0. In other words, we have phi 0, which is going to be the identity. That's where you start. So this is the function that takes x0 to phi of t. And then we have phi 1. Let me call that, I've had f over here, maybe f like this. And then what's phi 2? Well, phi 2 is phi 1 applied to phi 1, because when you start at phi 1 of something, you're going time 1 later. So this is, we call that f squared now, which means f composed with f. And we have this notation. So f to the nth in my language is going to mean compose a function of itself n times. And that's one way of getting an action which is discrete, but as the time is discrete. The other one, and this is what Poincaré first started doing, it's called a Poincaré section. And what that means is you take a transversal, you take a, like in, say we're in 3 space, we have a flow in 3 space, and look at things as they go out, and ask if they come back. And we have this thing, which takes this point to the first return to some section. So we've set some conditions and then look at things coming back. And that gives us also a homomorphism, but now from the section. So this is just background. I don't want to get into this in great detail, because the work I'm talking about is not R and it's not C. But this is another thing. And what Poincaré kind of initiated, along with other people in the late 19th century, it kind of got more important in the 20s and 30s, and really came to fruition in the 60s when I was in graduate school, primarily through the school at Berkeley and the school in Moscow, is looking at these things qualitatively. So, qualitative dynamics, or qualitative theory of differential equations, which is what we've called for a long time. Yeah, call for dynamics, which is what is meant by dynamical system. Is you look at, so given a point under this setting or this setting, you look at its orbit. So the orbit here would be all the points you go through time, and this is all the points you go through for time, which means these individual points that you get by iterating this function. And we want to look at the asymptotic behavior. And what does asymptotic behavior mean? Well, we try to study the accumulation sets or accumulation points, accumulation sets, points, sets, and orbits. And I'm not going to get into that, but there's a lot of stuff there. It's a very, very rich subject, and gets some crazy stuff out here. But in particular, there's some interesting ones on periodic orbits, which are simple and come up in this way very often. And I'm going to stop talking about, so for one of these, that would be a circle, an embedded circle. Something goes around, comes back to the same place. Well, because everything's stationary, means it's going to do exactly the same thing over and over. It's going to repeat. For one of these maps, it means that we have some iterate of the function takes the point back to itself. And once that happens, all the subsequent ones depend only on the residue class of the time volume. In other words, fn plus 1 of x will be f of x, and fn plus 2 of x will be f2 of x, and so on. So periodic orbit is the same thing as a finite orbit of one of these things. You just set up as 1, 2, and these play a huge role in this study, which I don't go into. Okay, so that's dynamics, and I will erase most of it. I was going to leave it up, but I think I screwed up. Now, the other object, that's my map. Now, and the object now is brains. So what's a brain? Well, think of taking This is the object that lives in 3 space. You take 2 plates, and you punch up 3 holes in them, the same number of holes here in the same places, and draw straights from one to the other. So think of something like this, and do a couple of colors. Red, yellow, and green. I hope they'll be visible enough. You know, I've got something here. So I've got 3 points here. And I have something going. Well, here I don't see it, but then maybe it goes here. And maybe this one goes, well, maybe it does a little tangle. It's up here. And this one, maybe it does that. Typical way. Well, the green and yellow are hard to slope rockets, but you get the idea. They're just kind of, and they don't have to end up where they started in this case. In fact, that doesn't happen. This ends up here, this ends up here, that ends up there. Okay? Now, what we do is we take this and then we allow the strings to flop around. So we're talking about deformation classes, homotopy classes of these objects. So we take a bunch of paths going. One way to think of it is I've got this plate crossing the unit interval, and the rule is things should move down. I shouldn't back up. I don't allow loops like that. Things just move down. Always they don't actually cross, and they end up, each strand ends up at one of your points. And that's called a break.
Can the set on top be identified with the set of holes in the bottom?
Yeah, and if you do that, you get a link or not.
Okay.
That's, yes. But we're not going to do that. We're just thinking of the passage from here to here. These things form a group, and in a kind of an obvious way. So first of all, let me just say, this is up to homotopy. In other words, I'm allowed to have things move. Now, this picture is supposed to be 3-dimensional, but really all the information is 2-dimensional. So let me show you how I think of that. Now I have my 3 points here. Let's say 1, 2, 3, 1, 2, 3. And what I know in this picture is I sort of look at it in a straight on and just see what's in front, what's in back when things appear to cross, because they're not actually crossing. So this one still goes down here. Then the second one, which was yellow, goes here, goes behind this, and then here goes in front. Goes down there. And the third one comes down behind that, over this. So there's a picture which captures everything about this. And the up to homotopy I want to illustrate with a particular thing. Well, I'll come back to that. So if I fix the number of strands, then I get, so here n is braids with n strands. And what I want to say, and this is a group. So this construction is due to Emma Martin, originally a paper in 1927 and 25, and then 2 big papers in 1947. So it's a relatively recent object in terms of people thinking about, oh, people have thought about this before. So this is a group. And how is it a group? Well, you squish things together. I'm going to do not that one, just something like maybe something like this. And let me use some more different colors. Like that. And maybe now I've got here something else which maybe goes here. And maybe that goes here. And that goes like that. So here's alpha, here's beta, and then here is beta. Very simple idea. Up to homotopy. Now, up to homotopy means that, well, up to homotopy holding the ends. So once I put it together, this stays, and this stays, but I'm allowed to move this one. This is no longer part of it. Okay, so we can do things with this. And in fact, if you look at this, I think this is a good example. and that's going to tell us what the group looks like. So first of all, there's some generators. And the generators are just single crossings. And so let me show you what I mean by that. Well, so let me give you a typical generator. I'm going to give you the one called tau 2. Tau. Actually, if I had 4, it would be better. Let me throw in a fourth one, just a white one here, which doesn't do anything, just to make it 4. Yeah. So then, this doesn't do anything. But what I'm going to do is, the first one doesn't do anything either, but the second and the third cross. That's the T2. So the T1, one crosses 2, this T2, the thing in the second position crosses, and then the T3. So in V4, there's 3 of these generators.
So you're always separating. So T3 and V3 crosses over.
Right. Ti is I crosses over I plus 1. At least that's the notation I'm using. And you can see that this is actually, you can just parse it. Right? It's a product of such things. Right? Any of these. Yes. You can always move the crossings so they don't both happen at the same time, and then you've written it as a product like that. T2 means, that whatever is the second one over is crossing the third one over, whatever that is. So, which is important for me, maybe not too. It's, I'm not looking at the colors. I'm looking at the positions. Okay, so these are the generators, and what are the relations? So there's basically one relation, or 2 relations. One of them is the following. I'll just draw a picture. I'll do it just in white. One of them is that if I have 2 crossings that have nothing to do with each other, so this is what? This is T1, T3, right? Well, I can move this up and move that down independently, so I can do this, right? And now it's all right, so T1 is now this is happening first, so it's T3, T1. Okay. So one relation is if there's no common strand here, which means what? That means if I minus j is at least 2, then Ti, Tj equals Tj, Ti. Okay. What happens if they have a common strand? Now let me do it with colors. In fact, I can illustrate with this one, except I've got, I've got 1, 2, 3 crossings, and that's exactly right. So let me just forget that this was here, and just take your finger and move that one over there. It's in front of everything. I can do it with no front. So what do I get? So now the red one is still in front of everything. It's going to essentially go down and then over. That's a land in the second place. That's where it's going. What do the others do? So the others, when they come down here, they cross. So we can think of this way. They come down and cross. And then they both come. So this goes here. And I hope I haven't screwed up my picture. I've got only 2 crossings. What's happened? I've forgotten something. These have to cross again because the green has green, 1. Bad example. Let me just do it. What I want to say, let me write down what I'm saying. It's Ti plus 1 Ti is the same as Ti plus 1 Ti plus 1. That's the relation, and the picture makes it very clear. So let's draw a picture of that. So Ti, so I'm going to say here's I, you've got strands here and here, but here's I plus 1, and I plus 2. Still don't know how I got that.
Orange would be above the green. Yeah, the orange and green would be.
Let me just, all right. Well, rather than stand here getting confused. So first of all, we have TI. Right. Then TI plus 1, well, I can just continue this down here and do the other one down. Right. This comes here and crosses here. And that one just goes straight down. And then TI again. So what's in this position crosses what's in this position, which is this. And the other one goes straight down. And I'm saying that that's the same as, first of all, these bring this crossing behind all of this up to there. Right, so I got that. Then what's in this position crosses what's in this position. So now we've got this. And that comes straight down. And now again, what's in this position crosses what's in this position, which means that. And those are supposed to be obviously the same. Because, look, I've just taken this, moved it over here, that's this, and this thing I've moved it across here. And our team showed that those two, so the presentation of this group is all the TIs with those two conditions. You can put them together into one, but it doesn't matter. So that's the group. And one can study two things about braids. I mean, you can study the braids as geometric objects. There's lots of interesting questions about them. Or you can study them as a group. And those of you who took the geometric group theory know about that, right? The B4 is very interesting. So there's a lot of theory of braids. And maybe I should just say that I'm going to be teaching in 250 on braids theory. I don't know most of the theory. We're going to be learning it together. There's a good, I think, a good book there. So we're going to read a book together about braids. Okay? But there's two things, and what do they have to do with each other? So how do I get from there to there? Okay, well, what I'm going to do is I'm going to go back to dynamics. We're not talking about braids for a while. And actually talk about the simplest kind of dynamics you can do. You don't need this one.
Right, quick question. Can a braid be, I'm just looking at this picture right now, I'm trying to imagine it as like the graph of a dynamical system, where as you go down, that's a function of time?
Yeah, I'll come to that.
Okay.
Well, if I have time. I hope I have time. I hope I get to the connection instead of just doing it. But let me start with some dynamics. And this is dynamics you may have heard of when you were in high school. You know, it's the last 30, 40 years, I guess. Actually, some of it goes back from. Okay? So I want to talk about the simplest possible setting for dynamics. So what's the simplest Euclidean space of the line? Okay? So I want to talk about one-dimensional dynamics. And for one-dimensional, I mean, a flow in the line is stupid, right? A flow in the line, everything just moves along, and there's nothing to say. It goes from minus infinity to plus infinity. It's like, or it stops. Maybe you have a finite number of things. You come to it, you stop, and then maybe the other one goes the other way. But it's a very simple picture. We have a bunch of fixed singularities in the vector field, points where f of x is 0. Those points stand still. They divide everything up into intervals, and on each interval things either all move to the right or all move to the left, or in the limit from one end towards the other. That's the whole picture of it. So we're not interested. That's kind of stupid. Homeos on R are boring, dynamically speaking. Okay? So there's two possibilities. So now I'm going to drop my capital F little f. I'm going to talk about, I prefer to use letter. I'm just taking it, for the discrete case, I'm taking a function from R to R, a homeomorphism from the reals to the reals, for the moment. Well, if f is an increasing function, if it's a homeomorphism, it'll be strictly increasing or strictly decreasing. This is the same as orientation preserving, right? What happens? Let me give you a picture. We have the same picture I just described for a flow. I have maybe a closed set. It doesn't have to be as simple as this one. Closed set fixed points. In other words, points that are taken to themselves by f. And besides that, what happens? Well, if there's no fixed points in here, then either f of x is always bigger than x or f of x is always less than x. Because we have something which is called the intermediate value theorem, which I like to prefer to call the fundamental theorem of one-dimensional dynamics. That, you either move to the right or you move to the left. If you do both, you have to stand still somewhere in between. So the picture maybe looks like that. That's the whole picture. That's boring. The other possibility is f is orientation reversing. So it's like a reflection. Okay? What happens then? Well, first of all, there is a fixed point, and there's only one. Okay? Besides that, you may have points that do this. They come here, and they land here, but this one comes back here. That's a period 2 orbit, 2 points for orbit. If you come back where you started, you repeat it forever. So you may have a couple of those. Or there's a homeomorphism, so they have to keep the order like that. Okay. And in between, what happens? Well, a typical point will maybe land here. Well, when it comes back, the point is f squared is a homeomorphism that's increasing. So when you come back, if you're in between two of these, and nothing else in between, then maybe you come down here. So that's like this picture, first return. Or in the other direction. So it's pretty much a structure with a little bit of stuff, but it's still boring. So we look at non-invertible maps. Now it's not just that this is boring, so we're going to get something more interesting. It's also, there are actual applications, reasons for it. In fact, the study of non-invertible mass, was going on before. When I wrote my thesis in '69, I was interested in exactly this, non-invertible mass of the interval. Everybody else was doing diffeomorphisms. And then in the early '70s, there was a paper by a population biologist at Princeton named Robert May, looking at insect populations. And insect populations where the growth rate depends on density. So when things get too packed, they die off. And so your standard model for a population with a constant growth rate would be given by f of x is some number times, so your new population is some number times your old population, 1.5, 50% growth rate, 50. But now what we're going to say is the growth rate goes to 0 if you reach a saturation. And if you normalize, that means, for example, something like that. Okay. So this is your growth rate at a given time. And the picture of this map is this. So this is 1. And a half is the maximum, and that height is alpha. This is called the quadratic map. The quadratic map. There's lots of quadratic maps, but this is the model. And this is much more interesting. Depends on what alpha is. When alpha is very small, there's not much to say. But when alpha gets up to like 4, so this is actually here, what's it saying? It's saying that this half goes all the way across here, and this half also does. So this point gets over here. This goes to 0. 1 and 0 both go to 0. And now you start getting really interesting things happening, like lots of things. If I divide this up into 2 parts, left and right, then unless I actually hit this point, I can describe what's going on qualitatively by giving a sequence of L's and R's, telling me where, start here, the point goes here, maybe it's here twice, 3 times, then I come here, and you write down a sequence of these letters that describes what the point is doing. We're not interested in exactly where it is. Turns out that in this example, give me any sequence of lefts and rights, when it's up to 4, any sequence of lefts and rights, there is a point, at least one point, that does exactly that. So I can get something that stays here for 1 million times, then goes here for 3 times, and then here for 2, and then here for 5 million.
So any finite sequence or infinite sequence?
Sorry?
Any finite sequence?
Any infinite sequence. Okay, so these are called itineraries. Okay. Sequence of L and R described or specified where, no, describe where f n x. For each x, I get an infinite sequence, and all infinite sequences actually occur for the right values. This is a very rich example. A lot happens here. So it's totally different from this. Certainly not boring. There are times when you can get a canter set of things that are interesting. Okay. In particular, we have so for alpha equals 4, every sequence occurs. Is and actually, that's kind of easy to see. You'll see a limited version of it in a minute, so rather than repeat it. So you'll see why quite easily. But in particular, we have periodic orbits and periods. In other words, it's not just infinite orbits, but in fact, every integer occurs as the period of some. Give me a number, like an integer, 25. There's at least one orbit consisting of 25 points. Now, you should be a little careful. We left the world of actions of C. This is an action of a semi, just of the positive integers. We don't have inverses. So just because you land where if you land where you started, then you go in a circle. But you could go for a bit, land somewhere, and then come back to that place without ever coming back here. That's called an eventual pyramid. Once you get here, you repeat this part over. It's not relevant to what I'm saying, but it's just part of the picture. It's different from the homeomorphism stuff. Okay, so this is a phenomenon for this particular example. And then in 1976, I believe it was, 1976. So, by the way, this field was not called dynamical systems. It was called, like, nobody had a name for it. Qualitative theory of differential equations, which this sure as hell doesn't look like. That's what it's called. So 1976, there was a paper by in New York. I think none of you were around when York gave one of the mini lectures a few years ago. And it's a paper called Period Fluid Wise Chaos. Okay, and what did they prove? Well, they proved the following. Now, they proved a lot, but this is the thing that made it famous, the title. If any continuous function given any continuous function, if has an orbit of period 3, well, they said a lot of things like that, but in particular, then for every n numbers, it also has simple elementary, and it's the spirit of this whole thing. So here's proof. Now they proved a lot more. And I should say, sometimes this stuff is called chaos theory. It comes directly from this time. This is where the buzzword chaos theory is going. Okay. So up to mirror image, I can think of the first line like this. I can think of the first one going in the middle going the second going to the first. There's the mirror image, which is, you ask where does the middle one go? And then that shows it. So it goes to the right. The argument is the same for that. Okay? Now I'm going to do something like these itineraries, where I'm going to use the division into these two. We call this L and this R. Now this orbit, of course, it's in L sometimes and R, sometimes it's in both. But I'm not interested. I'm interested in other points. So as long as something doesn't land on this orbit, it has an itinerary consisting of L's and R's. Okay? And which L's and R's can occur for this map? Now remember, all I know about the map is this. So what does this tell me? I know it's continuous and I have these 3 points. Well, I'm going to do a graph. So I'm going to draw a graph in the following way. I'm going to say one interval. The intervals will be the vertices, and I'll have an edge going from one to another if the following is true. If this is AB, if J is between, so I've got some map with this property is between FA and FA. All that's saying is that the image of I actually maps across J. So I don't know if these 2 points match different sizes of these 2 endpoints of this. So what is the graph here? Well, it's easy to see. Here's our vertices.
Your intervals are only the intervals given by the periodic coordinates.
Yeah, I'm saying this is one interval, and this is the other. Well, let's look. This goes here, this goes here. So L is an arrow to R. What about R? Well, it's a little more complicated. R does that. This goes here, but this goes here. So L goes to both. So the graph has an arrow here and a loop here. Now, if I have an itinerary, what does that mean? That means I go through a sequence of these. I can think of it as a path in here. I claim that every path in this graph represents an actual itinerary for any map with this phenomenon. All I know about F is these 3 points. The point is that once you go here, then there's a subinterval of this which actually maps right onto here. And then you can ask if I have, it goes, I'm not using L and R because I don't know which one's there. So like that. There's a subinterval of this that maps onto here. There's a subinterval of this that maps onto that subinterval here, and therefore onto this in 2 steps. And you use that kind of argument to say every infinite sequence is the itinerary of some point. Every infinite path in here. Furthermore, if you have a closed path, a loop, what's it called, a circuit in this, then it represents a periodic orbit. Because what you have is a subinterval of this rod which maps onto itself. Okay, you all know that if the Brouwer fixed point theorem, right? If the one-dimensional Brouwer fixed point theorem, if an interval maps into itself, it's got a fixed point. Right? Well, I mean, true, but the fundamental theorem of one-dimensional dynamics says if one end moves to the right and the other moves to the left, then there's a point that stands still in between. So you look at f to the nth and suppose this one maps this way and this one maps this way. Okay? So following a loop, or not a loop, but a circuit in this graph, gives you a fixed point of that inlet. And if the circuit is not the same circuit going over several times, then that's the least curve. The different itineraries can be different. So all you need to do is that there are circuits here of arbitrary length, which are not repetitions of shorter ones. Well, that's easy. 1, 2. Okay, now what about 5, for example? Well, go 1, 2, 3, 4. That's not the repetition of anything else. Okay. So by playing just with that, you know, I just proved that I can get a loop. Yeah, I keep saying a circuit of an irreducible circuit of any length, and therefore I have orbits of interference. Okay. Now this is a typical argument in this kind of stuff. You can almost see how that, we've got plenty of little symbols here. But here, the corresponding graph is L goes to R, and R goes to R, and so it adds another thing here, and you get lots of stuff. Well, the other thing is to notice that has a period 3 orbits, so this is lots. Okay, well, it turned out, and this was a theorem that was very popular. It appeared in the Monthly, and it's probably one of the 10 most cited papers in the Monthly. But it turned out that they had actually rediscovered the wheel. That in 1964, Sharkovsky, and there's lots of questions how to spell this, so let me tell you how to spell this. That's how it's spelled. In German, it's S-C-H-R. S-C-H, and it's people write two I's here instead of a Y. It's all the same guy. What he proved is a wonderful theorem, amazing theorem, I think. It says the following. I'm going to write down a crazy ordering of the positive. I'm going to put the powers of 2 starting on the right register. The first power of 2 is 1. So 1 is not 2. Then I'm going to do, that's not what I'm going to do. From 2, then 2 squared, and so on. Then we start on the left. I'm going to do 2 times the odds. I'm going to do the odds. So 3, 1 is not an odd, it's a power of 2. Okay? 3, 5, 7, 9, not just primes, odds. Okay? Then I'll put in 2 times there. 2 times 3, 2 times 5. So keep going, higher powers. Okay? Okay, well, so you got an order. Big deal. Linear ordering of these functions. Sharkovsky's theorem says take any continuous function and continuous map the line to itself. Find a periodic orbit of it. Find its period here. Then every period to the right of it also appears. So what Lee and York had proved was that the 1 over here should be a 3. Okay. The proof is much more complicated than what I gave you, but this is the kind of argument. You look at graphs, you look at how graphs, what kind of graphs you can get, and so on, and you prove this theory. So it's a pretty amazing theorem. Okay. Well, and also the second thing he proved was that if you take any particular place that exists in that, with exactly this and everything here, and none of the ones is the same. And that includes, if you think about this, you have the powers of 2 down here, you've got all the elements in this one. There's a division point which we call 2 infinity. It's not a real period, but there is a map which has only the powers of 2, but only. That's called the Feigenbaum map because Norrie's cousin, it is Norrie's cousin, Mitch Feigenbaum proved another wonderful theorem that I won't tell you about these things.
Sorry, so that doesn't follow from what you said before. So is it also true that you can sort of cut in between any 2 numbers here and get everything to the right?
That's the same thing. That's the same thing. If you cut between 2 numbers, you're saying you've got 9 and everything to the right. Okay. I'm saying pick any place.
I mean,
the only thing that's
because that 2 to the infinity is not cutting between 2 particular numbers.
That's true, but it's a division point.
Okay.
So any division point, but for most of them, we're thinking about in here a division point is just picking something. But you're right. For example, there's something which has all
the non-odds, for example.
Well, let's see. If we take something, yeah, all the non-odds, but that will be starting from here. This is the lowest of those. I mean, 2 is already there as a power 2.
Okay.
So it's really
Okay.
this.
Yeah.
The only one that's really different is this.
Okay.
Okay, so now, this theorem, which was, I mean, these guys discovered, they met Sharkovsky. There's a nice story in Line's book about chaos. They met at a conference in a boat in Vienna. And then this Russian came up to York and started yelling and screaming to him. He was talking about, he told him, well, you stole my theory. And it turned out it was right. But the point is, this was the famous one. And later people realized this, of course. This was known to everybody on the other side of the Iron Curtain on this stuff. Well, what this gave rise to a lot of very silly papers in the scientific literature. Because this was really about one-dimensional dynamics. And you got papers finding orbits of period 3 in some fluid flow and saying, therefore, you've got chaos. Which is crazy. This is really a one-dimensional theorem, and let me tell you why. So, we will hope I'm going to be able to get to everything, at least to the key things. Give me any n other than 1. So 3. 3, okay. Well, rotate R2 by 2 times 3. What periods have we got? We've got a fixed point of the origin. And a period 3. And that's it. Everything is period 3. So surely there's nothing like Sharkovsky for higher dimensions. That's the point. So all those scientific figures are crazy. Okay. But it turns out that there is something that does carry on. And that's a little bit. I'm going to run out of time. Let me see how far. So the proof of this theorem, or this technique of proof, which is really, I think Sharkovsky's methods were maybe not as nice looking as this, but the same basic idea, actually does more. It says the following. So what we call combinatorial evidence. So that's the following. Suppose I have any periodic, I'm back on the line. Suppose I have a periodic order. So on or in R. And I'm going to associate to it a cyclic permutation. Namely, write down these things, index them spatially. So say x1 less than x2 less than x3 up to xn. That's my periodic order. Then the action of the map is a permutation of these. So I can say define a cyclic permutation by f of xi is x of theta I. In other words, just look at what you do to indices. That's a permutation. That's all I use to build this graph. So take any permutation, I can build this kind of graph. What it says is, I'm going to divide down not just into two things, but n-4 variables, but I'm going to say, first of all, that my vertices are the gaps between successive points, and there's an arrow from one to the other if the images of this bracket the other. Okay? Just like what we did here. And the same idea, you look at the graph, you look at the itineraries, or you look at the closed circuits, and you can find out what other periodic orbits have to be there. For every single continuous function that exhibits this permutation. So any periodic orbit that looks like this forces a lot of other stuff. And that's like a partial order, not just on cyclic permutations in one order, but all cyclic permutations. Certain cyclic permutations force other cyclic permutations in these given indices. And that's a very rich structure. It's a partial order set. And there's a few nice theorems about it. One of them is that the only way that you only force finite many things is, in fact, well, that comes from Sharkovsky, essentially. To finite many things, this has to be power of 2, and you have to have a special shape. Namely, it has to be to the nth, and the right half and the left half have to interchange. And then under the first return, each half has to interchange its halves, and so on. It's called a simple order of periods to the nth. And those are exactly the things that don't force anything else. So let me just give you one quick example. This is period 4. Sharkovsky would tell you nothing except that 2 to the second forces 2 and 1. But an orbit like this, what's the graph? Well, it's A goes to B, goes to C, and C goes to everything. Well, right in here, that period 3 is today. So this one forces a lot of stuff, infinitely many different things, even though it's only period, it's only here in this order. So this is much richer. This theory has an L1. I wonder if it will take 2 minutes. So There's one other thing. Sharkovsky said there's almost a map exhibiting any of these. Well, there's a simple map that exhibits this. And what is it? Well, let me just, I'll graph the permutation. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. And then I join the straight lines. This is called the connect the dots map for officers. This map exhibits exactly the stuff you get from this graph and nothing else. So this is the simplest map with this particular dynamics, dynamically simplest. Any map that has this picture has all the dynamics that this has. All of it. May have more, but it certainly has that. That carries over. This is a real surprise because of this period of rotation. So the way to think of that is this. If I take any map which has those 4 points, its graph has those 4 points. Somebody would like, well, it's a graph, so I don't want to type that. Well, the fundamental theorem of one-dimensional dynamics says if I have this going to here, then some piece of this goes here. It's the same idea. So this tells us about any map. Think of one of these as a deformation of this one, but holding these points fixed. So the theory in dimension 2 is, suppose I have a periodic orbit. P is a periodic orbit. And now I should just say, when we go to dimension 2, we go back to homeomorphisms. There's a kind of meta theorem that whatever happens in flows in one dimension happens in homeomorphisms one dimension lower, and in maps, general maps, one dimension lower. So in one dimension we want maps, we're going to do this. So a periodic orbit, and now look at, so of F, look at this, which is all deformations mod, meaning don't move, keep that orbit, but other things can move around. Take your original thing and deform it a little bit. Okay, well that is a name. It's called a mapping class. And those of you who are around when Dan Marlowe was around know all about mapping classes. And there's a theory which turns out to be non-empty about one mapping class forcing another. What does that mean? That means if I have, so what I'm really doing is I'm puncturing the plane. I'm thinking in terms of the plane, but any surface at these points, and then looking at homotopic, isotopic class or homeotopic class homeomorphisms in that surface with those points in here. One forces another. If there's another periodic orbit where when you put these back and pull these out, that's the other class that's forced. So there's a forcing of these things. Okay, now where do braids come in? Well, that's back to Kevin's question. If I have a map, a homeomorphism, so this goes here, this goes here, and I'll get to that, okay? Then I can do the following. I can take this picture. This is a topologist trick. It's called the suspension if you're a dynamicist. It's called the mapping torus if you're a topologist. Take this and glue it to here using F. If you've taken algebraic topology, you know what I mean. But just imagine, these points are identified with these by some homomorphism. Just glue the identified points. It looks sort of like a torus if it's been twisted around. But these lines now become part of a flow. You actually have a flow here, for which the Poincare section is exactly the map I started with. So any homomorphism is the Poincare map of some flow. I can construct it from. If I look at what I did over there, I have a particular periodic orbit. And I do that, well, I can think of it, I can now think of, instead of gluing this like this, make these the same, and somehow I'm twisting this stuff. And then I get a braid, which describes what the periodic orbit is doing under this suspension. And so the idea is one can try to study forcing on braids, in fact. But it really comes from this idea, which comes from that. And I was going to describe a little bit of what Mauricio and I and a guy named Diego Benedetti did about 20 years ago, trying to understand some of this. Let me just, one more thing and then I'll quit. There's a big theorem in mapping class theory, which says that these are a group under a composition. It says there's a notion of reducibility, which means you can cut this up into pieces that kind of get moved around. If something is irreducible, then it's either periodic, which means it is a deformation of something which is really periodic, has a power equal to the unity, or it's something called pseudo-Nosov. There's a model of something called pseudo-Nosov, a very rigid kind of model. And it turns out that the pseudo-Nosovs and the periods are exactly the ones that exhibit everything that's forced. So they're like the connect the dots maps. And Mauricio and I and Diego had tried to understand at that time the Nielsen-Thurston classification, what I just described. There was a very famous paper that you've been talking more about, the Bestina-Handel algorithm, which decides whether something is pseudo-Nosov, does a lot. We came up with another algorithm, and it was based on the braid group. It was based on looking at the conjugacy problem of the braid group, which I can't go to because I'm way over time. And at that point, I just felt, I think this is a lovely group. Not just a group, but the objects are fun. They're geometric, and some of the other things I've tried to do with them are really not so much the group theory as the geometry of these things. So that's where I'm coming from, and where I got to. And I'm sorry I don't know if it was interesting.